Hello, everyone, and welcome back to the good stuff that we have been doing. Today, we're going to look at this well known integral called the series integral. Now, this integral right here is well known, of course, and I think the earliest I can remember is from the 1885, I believe, exam from the University of Cambridge. Although it still appears in MIT Integration B exam for 2008, I believe so. And even I think this also appeared in Putnam exam as well. So, but it's well known. And though the solution to this integral, I think out of main there are so many solutions. There's some because of one plus one over because of one over x squared, you can maybe use integration by parts to relate this to tan. Then some may involve Fourier series too, but I think the quickest is the one you do x equals to 1 minus t over 1 plus t. Yeah, that is the quickest. I think this one is like two lines, you're done. I'm not going to show the solution. And the motivation behind this is because the x, of course, will be negative 2 dt over 1 plus t squared, and it gets the job done instantly, I believe so. So that is the good part about this substitution. But we're not going to try this substitution. We're going to solve this using the double integral method because it's my favorite integration technique. And how does this double integral method works? Well, it begins by observing that first of all, the logarithm of 1 plus x actually is equal to the integral from 0 to 1 of x all divided by 1 plus xt dt, not the x though, the t. And to show this, just take u to be xt. Notice that if t is 0, u would be 0. So u would go from 0 to u equal x, because if t is 1, u would be x. Then notice that the u would be x dt, which is the top. So you basically have the integral from 0 to x of u over 1 plus u du. No, 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 not u, just 1. Then you would have the logarithm of 1 plus u. Then you are going to move this from 0 to x, which is basically the logarithm of 1 plus x. So this is a well-known formula, but we're going to see in this integral, we're going to remove this logarithm of 1 plus x and plug in this integral. Now, this may look very counterintuitive to many, but sometimes in mathematics, you have to complicate to simplify. So you would have this is equal to the integral from 0 to 1 of 1 over 1 plus x squared. Then instead of logarithm of 1 plus x, you would have the integral from 0 to 1 of x over 1 plus xt dt, then dx. Then you would write this as the integral from 0 to 1 times the integral from 0 to 1 of x over 1 plus x squared, 1 plus xt, then you have dt dx. Now, all that remains now is to do some partial fraction decomposition. Now, observe that I have done this previously, so I'm not going to waste your time. If you decompose this into partial fractions, you will have 1 over 1 plus t squared times x plus t. Then you have 1 plus x squared minus um, t over 1 plus xt. If you multiply the top, you are going to have x multiply this, you are going to x plus x squared t, and t multiplies, you're going to get t plus xt squared. Now t multiplies, you're going to get minus t minus s squared t. So basically, s squared t cancel out s squared t cancel out t, you would end up with uh, okay. Okay, t cancel out t rather. So you end up with x and xt squared. So you end up with x 1 plus t squared. And this 1 plus t squared would cancel this 1 plus t squared. So you see that this is the partial fraction decomposition. Now, we can write this as the integral from 0 to 1 times the integral from 0 to 1. Now you have this expression of 1 over 1 plus t squared, then you will have x plus t all divided by 1 plus x squared minus t all divided by 1 plus xt. Then you would have dt dx. Now, what we need to do now is that we're going to now this integral, both of them are convergent, so we don't need to worry about divergence here. So we can bring out a 1 plus t squared. So you have, first of all, the integral from 0 to 1 of 1 over 1 plus t squared. Then we can switch the order of integration. So instead of starting with the t, we're going to start with the x. So you're going to have the integral from 0 to 1 of x plus t divided by 1 plus x squared minus the integral from 0 to 1 of t over, sorry, dx, of course, of t over 1 plus xt dx. Then you would have dt. So what we have done here is to do partial fraction and switch the order of integration. Now next, what we do here is, this is 0 to 1 of 1 over 1 plus t squared, but then observe that for this particular integral, let us do it straight. So times the integral from 0 to 1 of x plus t over 1 plus t squared dx and then dt. Then you're going to subtract the integral from 0 to 1 of 1 over 1 plus t squared. Now notice that if you recall back, this is actually equals to logarithm of 1 plus x. This is times, sorry, this is logarithm of 1 plus t, because logarithm of 1 plus t actually is equals to the integral from 0 to 1 of t over 1 plus xt dx. So this is actually equals to the logarithm of 1 plus t dt. Okay, so next now, this will be the integral from 0 to 1 times the integral from 0 to 1 of x plus t all divided by 1 plus t squared. Sorry, this is x. 1 plus x squared times the dx dt minus, now this is the integral from 0 to 1 of logarithm of 1 plus t all divided by 1 plus t squared dt. Notice that this is actually our I. This is actually equals to I. This is actually our original integral, only that in this case now we have a t instead of a x. Now, notice here that by symmetry, notice that if you exchange x and t here, if you exchange the rows of x and t, this integral will not change. You understand? So basically, this integral will be twice the integral from 0 to 1 times the integral from 0 to 1 of x over um of times s of 1 plus t squared or 1 plus x squared dx dt. So no need to put x plus t. We can replace x plus, we can set x equals to t at the top there. This is symmetry minus I. Now, if we bring I, that means if we bring I to the left hand side, you have 2I will be equals to twice. Now, we can these two integrals are now separable. So we can write this as, first of all, the integral from 0 to 1 of x over 1 plus x squared dx times the integral from 0 to 1 of 1 over 1 plus t squared dt. So the integrals are now separable in that case. So the two cancel out. So I would be, the first one would be 1 over 2 logarithm of 1 plus x squared from 0 to 1, while the second one will be tan inverse of t from 0 to 1 as well. So basically, you would have 1 over 2 logarithm of 2 times, this is pi over 4. So basically, you will have pi over 8 log 2. So you see how everything simplifies nicely. So thank you for watching, and please do subscribe. I'll follow my page if you're watching from Facebook. Now, everything here has been done nicely. Like I said, this substitution is the best you can hope for, but I will not show the solution. I'll leave you to do that on your own. But after the solution, you can use the double integral method, and basically just plug in this integral, then you use partial fraction, and you're good to go. So thank you for watching. Please, thank you. Please follow me or subscribe to the channel. Thank you very much.